looking at the second half of chapter 6, a 250 kilogram boulder is pushed 12 meters by 320 Newton force. So we're going to calculate the work done. Okay, let's start by seeing if we need to convert anything. Kilograms, good. Meters, good. Newtons, good. All right, so let's make our list of knowns and unknowns. No conversions necessary. This kilograms is what? What letter? M for mass. 12 meters is going to be our distance or height, a D, and then newtons. Newtons is a force. It even says right there, so F. It's asking us to calculate the work, so our unknown is going to be a W for work. So when we look at our equations, this boulder is being pushed, okay? So it's linear work. So we have a linear work and we have a vertical work. So linear work is just force times distance. Okay. Now, notice we need just force and distance. So we need just these two guys. So that mass that they gave us, that's extra. Sometimes that'll happen. You don't necessarily have to use all the numbers given in the problem, and in this case we don't. So we're just going to plug in our force at 320 newtons and multiply it by our distance of 12 meters. So multiplying those together, how many significant figures do we want? It's looking like 2. So I'm going to get 38 and then 0, 0, because I just want 2 sig figs. What are the units on work? It's going to be J, joules, because remember, work is a type of energy, just like kinetic energy and potential energy, and they all have the same units since they're all forms of energy. In this case, joules. So this time we're calculating work again, but this time it's when a doctor is picking up a child to put them on the examination table. Okay, so let's start, same approach as all our other physics problems, and look at the units we have. Kilograms, meters, do we need to convert either of those? We do not, so I'm going to write my knowns and unknowns. I'm going to start with my 25 kilograms, and that is a mass, so I'm going to put M in front of it. What about this 1.2 meters? It says high. What is that? So it's either going to be a height or a distance. Okay, they both are measured the same. So I'm going to write D, I'll also write an H, because it could be either of those variables depending upon what equation we choose. And that's all it's giving us, and it's asking us to solve for work. Okay, but what type of work? So if you look at your equation sheet, we have linear, where work is equal to force times distance. So we used in the last problem. But we also have vertical. And for this one, it's still F times D, but the force isn't linear force, it's the weight force. That F sub W that we looked at in chapter 5. So what is the doctor doing? The doctor is lifting the child up. Okay, so let me draw a horrible picture here. So, I guess weirdly long arms, but here's the child. And he's lifting the child up. So it would be vertical, right? Along the y-axis, vertical. So this is the equation we want to use. Okay? In this equation, looking at what we have mass, that's not given in the equation. We have distance, that is. Okay? So what is F of W? So if you look at your chapter 5 equations and find F of W, it is mass times G. You remember what G is? G is gravity. It's 9.8 meters per second squared. So this is one of those problems where you have another piece of information, gravity, that's not given explicitly in the problem itself. Okay, so we're going to solve for f of w first using our mass given of the child, 25, and our gravity, 9.8, and then we'll plug that in to our work equation. So f of w is going to equal the mass, 25, times gravity, 9.8. So let's see the weight. How much does that child weigh on Earth? 245. I'm not worried about sig figs because this isn't a final answer, so I'm going to keep all the figures I can. So this is my f of w that I can plug in this equation here. So let's go back and use that equation now that we have our weight force and plug it in. So I have 245 for my f of w. My distance, so the doctor lifted the child 1.2 meters high. So multiplying those two together, I get 294, and it looks like I only need two significant figures. So the 2 and the 9 count. Look to the number next to it. Does that stay a 9? It does. Now I can't just stop at 29. I need a placeholder for that 4, but I need it to be a number that's not significant. So I'm going to put a 0 there. Now what are the units on work? Joules. It is a form of energy. So capital J for James Joule. Here we have a person running on a treadmill, given a velocity, a mass, and we're going to calculate their kinetic energy. So let's start and look at the units on the information given. MPH, do we want miles per hour? We do not. We want meters per second. So we do need to convert in this one. We're going to convert our miles per hour to meters per second. Okay, in this case, miles and meters, it's not metric to metric. So we can't use that KHD DCM. It's English to metric, so we need a conversion factor. And this is way back from chapter 4. The conversion factor to go from miles per hour to meters per second is 0.447 meters per second is equal to 1 mile per hour. So when we write this out, do our little railroad tracks, what are we going to put in this upper left-hand corner? Got 14 miles per hour. And we're going to take this conversion factor and we're going to put it here so that we're canceling out what we don't want and keeping what we do. So what we want to get rid of is the miles per hour. So we're going to put this 1 mph on the bottom so that they're on opposite sides of this horizontal line, thus canceling. That will put the 0.447 along the top. So to calculate, we multiply across and divide what's on the bottom. So we're taking 14 times 0.447 and dividing that by 1. And I get 6.258 meters per second. All right, so that meters per second says right here it's a velocity. So for my knowns and unknowns, I'm going to label that as V. The other piece of information is in kilograms. Is that okay? It is. So that's my mass. That's going to be 85. Okay. What it wants us to calculate, our unknown, is going to be kinetic energy. So these here are my knowns and unknowns. So once I convert, find my knowns and unknowns, I look for an equation. So my equation, there's only one for kinetic energy, and that is 1/2 mv squared. No rearranging necessary. Just going to plug in my mass, 85. My velocity, 6.258. And make sure to square the velocity. Okay? If you forget to square it, you're going to get the wrong answer. So 6.258, I'm going to square that. I'm going to multiply it by 85 and multiply it by 1/2, 4.5. Now I get 1664. Significant figure-wise, it looks like we're at 2. So 1, 2. Look to the number next to it. Does that stay a 6? It does not. It goes up to a 7. And for these two spots, we need to put placeholders, and those placeholders are going to be zeros because they need to be not significant numbers. And 0 is the only number that's not always significant. What are our units on kinetic energy? Joules, it's going to be the same as work because they're both forms of energy. This time, we're going to calculate the potential energy. Okay, so the last problem was kinetic energy because that person was moving, right? They were on a treadmill running at a certain velocity. And kinetic energy, by definition, is moving energy. Okay, potential energy is stored energy. So the object's not moving. So we're calculating the potential energy of a bird feeder that's just hanging in a tree. It's not falling, it's not being thrown, it's not moving in any way. So that's why it's potential, stored energy. Okay, so let's start by looking if we need to convert. We got kilograms and meters, that all looks good. So let's do our knowns and unknowns. So the 0.75 kilograms is what? The mass. The 4.8 meters, that's a distance or a height. Okay, they have the same units, different variables but same units. Potential energy is what we're searching for. And we only have one equation for potential energy, and that is mgh. Okay, so m is our mass, and instead of putting d for distance, they put an h, but it's still in meters, it's still the same units, still the same value. Now what's this g? It's gravity, 9.8 meters per second squared. Okay, so we have another piece of information that's not explicitly given, because when that bird feeder falls, when that stored energy is converted into kinetic energy, gravity is going to be what's affecting it, what's pulling that bird feeder to the ground. So that's why it's involved in this equation. So our mass is 0.75. Plug in our rate of gravity on Earth, 9.8, and then 4.8 for our height, our distance that bird feeder is hanging off of the ground. So plugging these numbers in, I get 35.28. But I want just two significant figures. So 1, 2, does that stay at 5? It does. And what are the units on potential energy? Same as kinetic, same as work, joules. So that will be our final answer. So here, we're going to calculate the power output of a 18 kilogram dog climbing stairs that are 5 meters high in a time of 20 seconds. So, conversions, this is supposed to be meters, so we're good on that. Kilograms good, seconds good. So now let's label these with variables, with letters. Come in second nature by now. So mass is the kilograms. Meters would be the distance or the height. So we have two different variables it can represent now. And then seconds is going to be t, time. We're looking for power. With power, we have several different equations, right? We have power is equal to mv squared over 2t. We have power is equal to mgh over t. And we have power is equal to, forgetting force, and just Fd over T. I think we even have another one. Can't think of what the other one is off the top of my head. But, so you need to figure out which equation is going to apply. Okay? So let's check out this first one. Mass, we have. Check. Do we have velocity? Distance or height, time. We do not have velocity, so that one's not going to work. Let's try this next one. Mass, do we have it? We do. Gravity, do we have it? Well, it's not on our list, but we know what gravity is, so we can have it. I mean, let's just add it. 9.8 meters per second squared. So we have gravity. Check. Do we have height? Yes, because distance and height are the same thing. Do we have time? So this is going to be the equation we can use. Okay? The last equation, we don't have force, so that's what knocks that one out. So let's use this middle equation and plug in what we have to solve. We have 18 for the mass. Our G, our gravity, is 9.8. Our H, height, is 5. And divide that whole thing by 20, the time it took the dog to get up that flight of stairs. So 18 times 9.8 times 5, and divide that whole thing by 20. So how much power output was required for that dog? Two significant figures. So 44, and what are the units on power? It's going to be watts, W. So it takes an Ironman challenger 15 seconds to push a boulder 5 meters using a force of 425. We're going to calculate the power in watts and horsepower. All right, so unit-wise, we are good. You pause it and double check. That first piece of information, 15 seconds, is a time. The 5.0 meters is a distance or a height. And then the 425 newtons is a force. It says right there, force. We're calculating power, but we're doing it twice, notice, because it wants it in watts and horsepower. So power, I'm going to put question marks, W for watts, and then power, question mark, HP for horsepower. So remember, you're looking at the equations on your equation sheet, oops, and picking out which one is going to work. All right, let's start from the bottom and work our way up this time. Do we have force? We do. Do we have VAV? What this is average velocity. I see no average velocity, so that's out. The next one, do we have force? We do. Do we have distance? We do. Do we have time? Yes, we do. Okay, let's go through the rest just to check. Do we have mass? No, we don't. I'm going to cross that one out. Top one, do we have mass? No, and we don't have velocity either. So this is the only one that can work. Sometimes you'll find two that works, and it doesn't matter which one you choose, you'll get the same answer. So let's plug in my force of 425, my distance of 5 meters, and I'm going to divide that by the time it took, which was 15 seconds. Now when I calculate this out, what are my units going to be? They're going to be in watts. So when I use this equation, the answer just comes out in watts. When I'm looking at my significant figures, saying 2, so my answer should be 140 when you put it in your calculator and round it to 2 sig figs. So 140 watts. So that answers the first part of the question. How many watts? Okay, but if I want it in horsepower, how do I get it in horsepower? So you'll notice the very end of your equation sheet, under all the power equations, there is a conversion factor to do just that. And it is 746 watts are equal to 1 horsepower. Okay? So to get from watts to horsepower, we're going to use that conversion factor. So you do your railroad tracks just like you do for English to metric conversions. What you want to start with is the number you're trying to convert. So I'm trying to convert this 140 watts. So I'm going to start that in my upper left-hand corner of my railroad tracks. I then am going to take this conversion factor and put it so that the watts are on the bottom part here, because they need to be on the bottom so that they're on opposite sides of that horizontal line, causing them to cancel. That's going to put my horsepower on the top. So to figure out my horsepower, I'm going to take 140 and divide it by 746, and I'm going to keep with two significant figures. So it's going to be 0.19, so I'm going to end up rounding it up, HP. So the last power problem we're going to try is using 25 horsepower. How much force is needed to climb a hill with an average velocity of 26.8 meters per second? So, convert if necessary. We have horsepower, meters per second. Okay, so meters per second, do we want that? Indeed we do. But horsepower. So when we're using our power equations, do the answers come out in horsepower? They do not. As we saw from the last problem, right? It comes out in watts. So if we have horsepower and we're using those power equations, we need to convert it to watts before we can put it in the equation. So my first step is to convert. I'm going to use that same conversion factor that was on the previous problem. The 746 watts is equal to 1 HP. I do my railroad tracks. What number is going to go up in this upper left-hand corner? It's the number I'm trying to convert, which is the 25. So this time, the 1 horsepower is going to go on the bottom because I'm trying to get rid of horsepower, so I need them on opposite sides of that horizontal line. This is going to cause my watts now to be on top. So in this case, I'm going to be multiplying because I multiply across. So I get 25 multiplied by 746. I'm not worried about significant figures because I want to keep all of them because this is not my final answer. So this, 18,650, that is my power. So for my knowns and unknowns, my power is 18,650 watts. What other pieces of information did they give us? Well, they asked how much force, so we know force is what we're looking for. And then an average velocity. Okay, so it's V for velocity, but it's got that sub AV because they specified average. And that is 26.82 meters per second. So looking to my power equations, which equation is going to help me here? We got 4. Top one, I need mass, don't have it. Second one, I need mass, don't have it. Third one, I need force, do I have it? Yes, that's one of the things I'm trying to solve for. Do I have average velocity? Yes, I do. So check, check. So I can use this one. Now what about this last one? Force, yes. Distance, no. So I'm choosing that equation, but notice I'm going to have to rearrange it because I'm solving for force. That's what's got the question mark by it. So I need to get force by itself. So that V average I need to get on the other side of the equation. So to get it on the other side of the equation, I need to divide by V average. So if I divide by V average, whatever I do to one side, I have to do to the other side. On the right-hand side of the equation, V average over V average cancels, right? Just like horsepower over horsepower cancels. So my equation becomes force is now by itself, and then I have power divided by average velocity on the other side. So now plugging in, power is 18,650. My average velocity is 26.82. So looking at my significant figures, once I divide those out, I only want 2 significant figures. which is going to prove difficult because I have 695. So in order to do 2 sig figs for this one, I would have to put it in scientific notation. So, what are units on force? Units are going to be newtons. Okay. If you're looking at sig figs, we just want 2. So I would have to write it like this. Okay, and I won't give you one where you have to do scientific notation in order to give me the answer correctly. It just happened on this problem here. So, all right, well that is it for chapter 6. So do the practice problems. There's an answer key posted for the practice problems as well before you take the chapter 6 quiz. You get 2 attempts on the chapter 6 homework quiz. So the first time, write down any of the problems you didn't get and try to work them out and maybe re-watch the video if needed.